All right, sorry for the delay. Hi everyone, my name is Yuriy Solodkyy, and today I would like to present a work that actually been done in collaboration with Dr. Stroustrup, Dr. Desreis, and Dr. Pirkelbauer back at A&M, and it's some thoughts about visitor design pattern, why we should start moving away, and why language is kind of ready to get facilities to do that. So I would like to remind just a slide from Dr. Straus's presentation on Tuesday, where he said, like, okay, in the language we should keep simple things simple. We should not make complex things like unnecessarily complex, and especially we should not block people from helping themselves. They should be able to do what they want to do. And we should never, or try at least, not to sacrifice the performance. So, as the outline of the talk, I'll remind what visitor design pattern is. This talk is not really meant as a bash on visitor design pattern. It's more of a discussion of what problems we have in the visitor design pattern and what alternatives do we have to resolve it better. This is not going to be a technical talk on how we implement a particular thing. It's more of a software engineering talk, like what kind of facilities it enables us to write code. If you would like to know more about the details of implementation, we have wrote papers on it, and we had earlier presentations at like C++ now, so you can look it up. But visitors they work, they solve real-world problems. Everyone knows that. But there are better abstractions to do to express the same kind of solutions for the kind of problems that visitor solves. And we would like to show two alternatives. One of them is pattern matching. The other one is open multi-methods. None of them is in the language yet, but we would like them to become in the language one day, and we would demonstrate pattern matching on a real library we've made. So excuse us for some of the quirks of the syntax that are just because it's a library. It's an experimental library, so the syntax we would like to propose eventually for the language will not look exactly like that. So don't get like worried about like the little. We would like to just present to show you what kind of facilities it can bring into the language, but don't like jump into immediate like something you don't like about the syntax. And open multi-methods, it's another work we did earlier. We did like an experimental implementation on top of EDG. Again, like I will not go into details. You can look up the paper. I'll just show like what kind of syntax it enables and briefly mention what kind of facilities it enables. So the goal is basically to compare the solutions, the typical solution to some common problems using visitor design pattern, and what these two alternatives enable us. Okay, so we know about visitor design pattern, I think, mainly from the Gang of Four book, and I will quote, call it, a visitor design pattern represents an operation to be performed on the elements of an object structure. Visitor lets you define a new operation without changing the classes of the elements in which it operates, which is, I think, the main definition. Oops. Okay. I should not touch that. For us, visitors, because visitors design pattern is often used in combination with other patterns like interpreter pattern or traversal pattern, people a lot of time look at it as this Swiss Army knife that does everything. For us, for the purpose of this talk, we will look at visitors design pattern only as a technique for performing like external case analysis. We will not be discussing something like how do you do traversals with it, how you mix it, but we will definitely demonstrate it on examples that originate from a use you will see in the interpreter pattern. An interesting thing about the visitor design pattern, it's even though like it was presented in the Gang of Four book on design patterns on using the polymorphic classes, it can be implemented in a whole lot different ways. Visitor design pattern actually became this interesting phenomenon where any language feature you add to C++, people will find a way to use it to do better visitors. Like we had templates added. People figure out, okay, I can ignore like virtual function calls. We had like when somebody invented something called polymorphic exceptions idiom, and that turns out to be probably not something to do, but it can be abused to do visitors. You've seen in this conference people like to put lambdas in tuples or something to also do this kind of. So no matter what language feature you add, you can turn it to do a better visitor. What we think is it's probably time to do something to replace visitor in the languages, except to kind of keep doing them better. One thing I would like to mention here, so for the examples we will use the polymorphic classes the same way it was presented in the design patterns book. However, most of these kind of issues I will mention in the examples, etc., they are applicable to other implementations too. Whether you implement it using a tag inside your class, or whether you do some sort of compile time resolution, etc., most of these issues will still apply. Okay. So what are the use cases for the visitor design pattern? Essentially, anytime we need to add a functionality to a class hierarchy, we can use visitors. Anything where you would use a virtual function otherwise, but something that you couldn't foresee in advance, that's a use case for a visitor design pattern. And other things, like if you have graphs of objects of different kinds, and you need to either figure out like what a structure of an object or links between an object, what kinds they are. That's also usually a good application of visitor design pattern. Any kind of interactions in games, like where you have different objects, those can be handled with visitors. Customization points, plugins, basically all these are use cases for regular virtual functions too. The only difference is that as we will see soon, sometimes you don't have oversight of all the possible things you would like to have in your interface. So I took directly an example from design pattern book where they use visitor design pattern in combination with the interpreter pattern, where they say, okay, you can have this language of your own and compose like terms and then interpret them to do something. Whatever customizable stuff you have. So here we'll be actually dealing with with Boolean expressions. So imagine an algebra of Booleans, and we would like to represent terms in this simple language and be able to do a few things about it, like evaluate it, transform, print, you name it. Like here, a small picture just demonstrates an example of a term. So it's basically we're not going to deal here with parsing per se, but we will assume we already have an abstract tree represented using some classes, and we will look at those. Any questions so far? So traditional object-oriented way is basically we would introduce an interface, and we will put a virtual function into that interface for any useful functionalities that we think we might need in that interface, as we can call it later, and override it on a particular variant of that Boolean expression. Examples of those things we can do would be something like printing an expression, copying, which most of us probably know it as cloning, like clone the entire expression. Evaluate an expression given a context. Context in this context is essentially just a map from variable names to values of those variables. So nothing too complicated, but we might want to evaluate that expression in that context. We might want to replace a sub-expression, replace a variable in an expression with another sub-expression. Another interesting case is like we might want to check that two expressions are the same, like deep tree-wise are the same, essentially. Or we might treat one of the expressions as some sort of pattern where let's say variables can match anything. We might want to implement a match function where we would try to match one term against the other using variables as patterns. Is this? So the note here to make is. Did we miss any functionality? I'm pretty sure like anybody has something extra to add to this interface. So no matter how many things you put, like there will be something more to do. And some of the things is like unify, replace the entire subtree, conjunctive normal form, disjunctive normal form. All these can be added, and I'm sure there are more. Okay. Once we've set in this pure object-oriented setting, once we've set up the basic interface, we will just then the variants, basically the concrete terms would be derived classes, into which we will have as members either the subtrees or like the name of the variable, of the value, etc. And then we just implement those virtual functions to do the concrete thing, to do that function on that particular expression. This is an example for not expression, but it's pretty straightforward. I'm not going to go into it in details. Immediately what we see here is like, should we group those by classes, like in when we do our traditional writing software? Should we group them by classes, or should we group them by functions? Because like when you do your case analysis, ideally you want to see all your cases together, which is not something typically we do in object-oriented programming. We usually group them by classes. So if you group them by classes, your cases are essentially get scattered around multiple translation units. So just to summarize this, the traditional object-oriented, well, the advantages of it provides extensibility of data, because it's very easy to add new essentially kinds of expressions, which is derived from Boole expression. It gives us all the traditional object-oriented features like modularity, encapsulation. It works in the presence of multiple inheritance, dynamic linking, so it supports well the object model of C++. The disadvantages of it, there is no extensibility of functions. So every time we would like to add a new function, we have to essentially change that interface, which is not something you can afford always. There's also no local reasoning, as I said, because these functions can be scattered around different translation units. And it's inherently non-relational, because we essentially do it on one argument. We cannot use it to compare like 2 arguments or 3 arguments, etc. Now, scratch actually that we have those virtual functions, because basically we would like to look how would we implement something like that using now visitor-Z pattern, assuming we cannot foresee all the functions in the interface. We would like to essentially design a visitor interface where we would implement essentially the same functionality using visitors. So we will still use the same class hierarchy, but assume there is no virtual functions, those virtual functions in it. Okay. So the first thing we do is we usually list our cases, which is basically our the kind of terms we have in the grammar. And then we define our visitation interface, which essentially does the case analysis. So it says like, okay, what should we do when we find this kind of expression or that kind of expression, etc. A note to make to yourself here is like it requires foresight of cases. So we essentially have to think about like what cases will we have. Another thing is this is important. I found it important when you have to teach this visitor-Z pattern. Don't use overloading unless you really have to. If you are using it just to teach students, they get it much better if you don't. Because if I can call all these methods visit, which is what people typically do, but it's not always used. And if you don't really depend on that, just call them differently so people can see what's going on, and it will save them a day or two in understanding. And that's what they do also in the design pattern book, which is they discuss that too. So anyways, I'll mostly present it with different names just for the ease of understanding, and I'll show a case where it might make sense to use the overloading. So once we define the visitation interface, we essentially then have to embed what's called the accept method into the actual hierarchy. So we declare this virtual function accept that takes that visitor, and then in every of the variants we override accept to essentially call it saying, hey, I am this case. Because in a particular accept we will know the exact type of this, or if it's not, or at least the most derived that we know of, and then we will call the corresponding visit method to say like, hey, I'm this case. So essentially we uncovering in the accept, we uncovering our dynamic type, and then we pass the dynamic type to the corresponding case. I'm sure everybody probably thinks that. So unless if you have any questions, so feel free to stop me. So a note to make to yourself here, it's intrusive. Basically, we had to change the boolexp interface to be able to add those functions. So this means that we cannot add this retroactively. If there is an existing class hierarchy, we cannot add. And the same happens. It doesn't. It's not true only about like this way of implementing visitor-Z pattern. If you implement it with tags or something, it's still going to be the case. It's going to be intrusive. Like if you don't have your tag yet, you will have to introduce it. You will have to define your visit interface, and then like somehow map your tags to the visit calls. So everything still applies, whether you implement it with polymorphic classes or with something else. And note here that it's also specific to the class hierarchy. So if we were to do visitor-Z pattern again on a different class hierarchy, we will have to essentially write this code again. So, okay. Now, having done the groundwork for the visitors, how would we implement something like eval, which takes an expression and the context and evaluates the value of that expression in that context? So, okay, just a second. I thought I had it, one thing here, but I guess I don't. Anyway, so what we do essentially is we derive a class which we call eval visitor from our Boolean expression visitor. And that class overrides each of the visit methods to do a corresponding thing to evaluate that specific class. We then make an instance of that visitor, and we call accept on the original expression and pass that visitor. A thing to note here is within the visitor we don't have direct access to variables of the original function eval, and we don't have we cannot directly return. So because of both of these are because of the control inversion, because we get called as opposed to we are already in that function. So because of that, we have to save our context inside the visitor and basically also save the result inside the visitor, which is what I highlighted there, like in this red color, and then essentially return that result. This is a common thing to do. The thing to note here, like when I ask, like why wouldn't we chain accept and visit to essentially return, let's say bool exp star, since most of the time here we do that. Well, that might work if you're in a language where everything is derived from a particular class, which is not the case in C++. And I'm sure you might have a use cases tomorrow where instead of returning, say, expression, you would want to return just a bool, which is like the result of this. And you might start parameterizing, but then your visitor interface becomes parameterizing over result, and that pops up into the essentially accept. And since we don't have parameterized virtual functions, that's not quite doable in C++ right now. You can parameterize implementations to do that and kind of reuse a little bit of this boilerplate, but still that's not the main thing. Any question about eval so far? Okay. So let's look at slightly different example. The main difference about this example and the handling of the visitors is that now essentially the subject is not a const expression. Okay, so the meaning we would like to give to this replacement is essentially we don't create a new data structure. We instead traverse this data structure, and if we find a variable with the name that we are looking for, we replace in place that variable with whatever we have to replace it. So clearly, this requires to have a right access to the objects in it. That's why we don't have const. That creates a problem with our current visitor implementation because, I mean, as soon as we try to take address of that uncovered type, it's I mean, you cannot cast const to non-const. Well, we can argue we can start const casting them and maybe pass always like a modifiable reference, but both kind of like more like workarounds. If you start const casting them, it's kind of like deferring the troubles, and like your code will get even bigger and harder to understand. Now, if we will decide to pass it by reference always by modifiable, then a function like copy, where I take a Boolean expression and would like to create a copy of it, there is no need. I need to have a right access to that function. I would like to have, but like with the requirement to have a mutable access to the, I will not be able to put the const on my copy argument essentially. And so one way or the other, like I will still have to do const cast somewhere. So to do it properly, we will. Okay, to do it properly, we will essentially have to add a new visitation interface, which is what we will call here a mutable bool exp per visitor, which won't have const, as you can see. and which might look something like this. So the regular visitation interface takes the expression kinds by const reference, and the mutable takes by mutable references. Now notice we have to implement two different accepts. One accept that takes the mutable visitor, and another accept that takes the immutable visitor. We roughly now doubled the amount of boilerplates that we have to do, right? Sometimes we can save a little bit. So most of the time, like your functionality where you really need to write, it's just in some of the cases that you need to write cases, but the remaining of the functionality doesn't really need to. So what people typically do is they use this trick called forwarding, where the mutable calls are forwarded to immutable calls on the regular visitor, and we derive the mutable visitor from the immutable visitor. That helps us to reuse sometimes some of the immutable visitors, and so that we can overwrite only those we're interested. Note to make here yourself, this forwarding technique is useful not only for this forwarding of mutable implementations to immutable implementations, but it's also useful for when inside your visitation interface you have both base and derived classes. So let's say you have instead of having like a value, you have now a trie value which gives like a third state to the value, and the trie value is derived from the value. So you can introduce the trie value into the interface and make by default it forward to the regular value or something like that. So yeah, is any questions on this? Okay, perfect. Come on. So what about the binary functions? So how would we implement something like equality of two terms, where we don't just want to uncover the type of one argument, but we want to uncover the type of both arguments and do something on those? So we start the same way. We essentially declare a visitor, which we will call an equality visitor, and instantiate it, call accept, pass the results, etc. What's not clear is what should we do in the middle, because once we uncovered the first argument, the second one is still uncovered. So we have to pass the uncovered first one somehow to know the second one. We do this essentially by parameterizing a new visitor over the uncovered type. And that helps us essentially to save the static type. The things to remember here, like these patterns will repeat a lot, so you can easily factor it out into something where you just pass a visitor name in and just do this sequence of operations. This is how this parameterized visitor will look like. So it will essentially take the actual dynamic type as an argument, and what it will do, it will forward to a function EQ, which is essentially just a set of overloaded functions, which I will show in a second. This is actually the first, I mean, in our examples, this is one of the useful places where it would have been useful to call it visit instead of calling it specific, because then instead of writing 5 of them, we could have just written 1. Why? Because this is, in case of equality, we are only interested in the cases where both types are the same. So once we uncovered one argument's type, we are only interested to overwrite the visit method on the same type, and to return false on everything else. Does that make sense? So, okay. So essentially, yeah, there are and especially if you like to use generic programming, it's good to call them all visit. But if you are presenting to students, don't. Okay. So so what basically the EQ does, that does the actual case analysis, where we have, okay, if they are both variables, just compare names. If they are both values, compare values. If they are both, let's say, AND expression, just compare left and the right parts. which is pretty straightforward. There is nothing super complicated. The thing is, I wanted to make with this slide. Okay, one thing before I go into the alternatives is note here that we've used 5 vtable entries for essentially each of the visit methods. And now we've instantiated 5 classes using those. So we essentially have now spent like 25 vtable entries. Why I'm mentioning this? And that's assuming only immutable visitation. So if we add mutable, then we have like 10 by 10 essentially. But like why I'm mentioning this, because a lot of times this is mentioned as why people don't want to use multi-methods, because essentially you generate like n to the power of m table. What we will see in the slides is that this does more. Like this generates more RTTI data than the multi-methods do, if you do it the visitor design way. You don't have to read this code. Essentially, this does the same implementation as we just saw for equal, but it implements match. The only comment I wanted to make by putting all this slide is basically that all these boilerplate codes that you see on the slide is driving to do this little case analysis there. So that's how much we have to write, and this is not reusable both it's specific for class hierarchy and it's specific for match function. So you cannot reuse much of this. You will have to write it over and over again when you have to add either new function or new class hierarchy. And you can try to reuse some bits, but it will complicate code again and makes it more complicated. So the things to take about the visitor design pattern is they provide us extensibility of functions, because we can now add new functions without changing the interface. They are fast. They take just 2 virtual function calls, which is better than a lot of other alternatives. And if you implement visitor design pattern using not virtual function, but something like tag dispatching, when you know your set of cases is closed, which is a pretty common case in a lot of scenarios, then it can be even faster. It's a library also solution, so we can help ourselves to basically do that. We don't depend on a compiler to implement it, etc. The disadvantage is it's extremely hard to teach to students. I was TA back at university, and I had to teach it to students, and it took them about a week of debugging to really understand what's going on and to be able to go and like this use it. With pattern matching, I can show them over in the class, and they will be able to use it after the class, which is kind of what I'm saying. It's hard to teach. It's also intrusive, as we saw, specific to class hierarchy, lots of boilerplate, there is control inversion. It also hinders extensibility of classes. What do I mean by that? We can still derive new classes from those that are already in visitation interface, but they will only be distinguishable as those for us as those cases we listed in the visitation interface. So we essentially we limit the set of distinguishable cases, let's say. Okay, any questions so far about the visitor design pattern? Okay. So let's move to our first alternative, which is the pattern matching. So what's a pattern? It's essentially usually a brief notation, a term that describes some sort of immediate predicate on an implicit argument. And implicit here is usually important because you can compose patterns, and they usually correspond to the composition of your subjects. What is pattern matching then? It's essentially usually a language facility that provides you the laconic syntax to do that, and that allows the compiler to generate an efficient decision procedure that will do that case analysis. Okay, that will do that checking. Examples of patterns we find everywhere, like wildcards, variables, like regular expressions. You can compose those into terms. You can see grammars as pattern too, because they distinguish, valid programs from invalid, where a program is essentially a subject. So we see patterns in a lot of different places. Why should you care? In functional languages where it's the pattern matching is super popular, pattern matching has been known like to drastically simplify code. Like there were documented cases where people, when they had to choose a language for the project, they chose a functional language just because of the pattern matching in it versus C++. It's not used only for these kind of like compiler cases. There is a paper where they also document, they chose, I believe, either Camel or Haskell for some sort of like trading. It's a company in New York, I believe. But yeah, you can do essentially high performance computing too with these kind of abstractions. It's not inherently kind of like non-C++. When is it useful? Whenever you need to perform an analysis of structure of your data, like, or at least part of it, that's when you will use it. So now I would like to show it on a real library that we implemented as a part of this experimentation. The library is not what we try to standardize or anything. The library uses quirks and different things you wouldn't want in the standard. But the library gives you a pretty good idea what's possible and efficient, actually. This is more efficient than any other alternatives for pattern matching we found in C++, and we have performance results in the paper, so if you are interested in that, you can look it up. I'll have just like little performance, one slide on it, but you can read more on the details. So don't take it as an actual syntax that we are proposing. Take it as a syntax we use to experiment with what's possible. Okay. So the library is called Mach7. It's available on GitHub if you would like to try it. And essentially, the code I'm presenting both of visitors and the pattern matching. It's there. It's in files that start with CppCon. So if you want to kind of read those, like those are the ones you should start from. It's still kind of a student project. It's not polished to industrial standards. So I apologize for that. I don't have too much time to maintain it, but I'm trying. But yeah, if you ever want to look at it, start from those CppCon files. So what the library brings us, essentially, the library is it's a library solution to pattern matching. It's open to new patterns. What it means, it's that all the patterns in the library are user definable, so you can add your own new patterns to the library, and you will be able to take advantage of the efficient match statement that I will show in a second. The patterns are first class, so you can save them in variables, pass to functions, etc. They are type safe. It will, let's say, most of the time report incorrect application. Like we have like a lot of static checks there whenever we can, so that you don't get like all the templated errors on yourself. So it's pretty reasonable. Just to give you an example, I first wrote all the examples in visitors, and then it took me about 1 hour, 20 minutes to rewrite everything using the library. And of course I had errors during that, and the errors were quite understandable. I could figure out from, of course I wrote this, so it's probably easier, but in all of the errors I had some indications what went wrong. So hopefully, of course your mileage might vary, but hopefully it's not going to be too bad. It's non-intrusive, so you don't have to change anything about your classes. You can add it retroactively. It works. What's more important, why we think it has a chance to sometimes become part of the language. It works with the existing C++ object model, so you don't have to change anything. It works in the presence of multiple inheritance, both repeated and virtual. So all that works, and it's actually very efficient. It's faster, sometimes a little bit faster, sometimes a little bit slower than the visitors. If you are talking about the case analysis on essential dynamic types, but it's not limited to just constructor patterns. As I said, it can take other patterns too. So with this, how do you work with the library? Essentially, and parts of it you will also have in the language solution. So we have our old class hierarchy where we don't have anything else. And what we have to do is to be able to do decomposition of those patterns, we have to tell the library what to match against in the first position, what to match against in the second position, etc. So that's kind of like if you looked at C# is getting pattern matching into language soon, and they have like I believe it's like is operator, which goes kind of like the Scala way, where you can define what it should be when you extract. So this is our way of doing that. Bindings is basically for us to say which member to extract in a given position. So members is essentially something that generates code there. It doesn't have to be data members specifically. This can be freestanding function taken as an argument, the class. This can be a member, like nullary member function, so everything. And this respects access control. So you only get access to like public members, etc. So this respects like encapsulation and everything. And then you just have to say, okay, which of the existing patterns like you would like to use in case you just want to reuse some of them. So point to note here, it's non-intrusive and respects member access, as I said. So how would we implement the same eval using this pattern matching library? Essentially, because in C++ we don't have implicitly introduced variables, like I have to declare like variable patterns explicitly, which is what we do with these red ones, which are the patterns, the variable patterns. But once we did that, we just do a match on the original expression, and we do, okay, in case it's C, actually, no, I was worried for that. Okay, so basically between case and C, there is still a parenthesis. It's just like I was trying to make it less of a color, but I guess here you can't see it at all. So case, in this case, but right, like it is right now, it's probably closer to what it will be in the language, so ignore that. But yeah, there is extra parentheses there. So we do essentially, and we say, okay, if the expression is variable, bind whatever the name of that variable into this pattern name. If it's a value, bind whatever the value of that actual value expression to this variable pattern value, and etc. for like sub expressions of each of those. And then we just essentially do our traditional stuff. So for the case of variable, we just return its value from the context. We return the value, the actual value itself, or we pass recursion forward to recursively call ourselves on sub-expressions. And that's essentially everything that you have to do to implement the same eval using this library. Any questions on this? So the note to make out of these slides, those same like whatever brownish color, these patterns, they act as patterns in the left-hand side, so they match stuff, and they act as values in the right-hand side, because you saw I could use name in the right-hand side, and the right-hand side I mean like the imaginary lines that divides returns from the case statements. So you can use them both as values and in the right-hand side as patterns in the left-hand side. There is no control inversion. Your returns are real, so you don't have to save your state, etc. And you get direct access to arguments. So we didn't have to save like context. We just access context directly from the argument list. So the issue we saw with replace, where we wanted to have essentially immutable access to the tree, it's even easier here. We don't have to do, just because now the subject where is mutable. What's happening here actually? Once we recognize a particular pattern. The library introduces implicitly a variable called mac and position, and the type of it is the same as a reference to the type in the constructor pattern. So what happens here, if the subject was originally const, that reference will be const. If the subject is mutable, the reference will be mutable. So we don't have to do anything essentially to distinguish, mutable cases from immutable cases. We can now assign to parts of those discovered cases and drive our recursion further. The point, that's the point I just said, that the immutability of the uncovered subject is the immutability of the original one. Now the point is here, what I want to say is also in this case we have to forget about the fall-through behavior you have in the usual switch statement. Why? If you look at the last two cases, the code syntactically looks exactly the same. So you would imagine like why shouldn't we be able to just fall through? The thing is, yes, it's the same. However, the type of match 0 is a reference to AND expression in the first one, and it's a reference to OR expression in the second one, which is why we can't reuse it, because potentially those can be completely different objects and stuff. So this is actually similar to how I showed the example with equality. The reason I'm trying to show here an example of how to do the match is because you remember I had a slide how much it takes to implement the match using the visitor's end pattern. This is everything you need to do to implement that same match using the pattern matching. What's happening here essentially, instead of doing a pattern matching on one argument, we now do pattern matching on two arguments. One of them is P, another one is X. Okay, and then we correspondingly have two sets, two patterns for each of those. So what we are saying here, if the first argument is a variable expression with a given name, and the second pattern is anything, which is our instance of the wildcard pattern, check if it's already in the context. If it's not, just copy it over. If otherwise, check it's the same. Then otherwise, if it's value expression, check that the other value expression is the same. That little plus you see, it shows kind of like that set of patterns is extensible in the library. Plus is what's called combinator. So it's an operator that lets you compose new patterns out of existing patterns. What it does, it says, okay, once the variable pattern value was bound in the first argument, use it as a value pattern in the right-hand side. So basically make sure it's the same in the right-hand side against what. So what that second case say is like, if they are both value expression and their values are the same, just return true. And similarly further, like if they are both not expressions, we just drive the matching further on the essentially subparts, etc. So pretty much the same as the same implementation will be for just equal. But you can see instead of having these pages of stacks, this is everything that you need, and that's exactly the same. You can compile both of those files on GitHub and see, and it's actually faster than visitors. And we'll see it in a couple of slides. So. What else can we do with it? Here's something you can't do with visitors. Imagine like we would like to implement some, this is of course not the entire algorithm, but imagine like you would like to implement something like disjunctive normal form, where you would have to look at the structure of your expressions. So you might want to say, okay, if my expression is kind of like the Morgan law, like if it's not applied to some expression, I can just drop the two nots, okay, and return E. If I have a conjunction of something and a disjunction of something, then I may want to redistribute over disjunction, and same for the second argument. So this is essentially everything you need to write to be able to express these kind of nested matches. And the library will generate code essentially to actually destructure the subjects and do the pattern matching on those, and do this. Of course, visitors don't help you with nested matches because visitors just help you to uncover the highest level, but they don't deal with the structure. Of course, you can start implementing kind of like what we did with the match function, but that's already kind of moving it into runtime. Like this is all generated at compile time, the decision procedure. One thing also that I was getting several times, like people were asking, can we do something like this on boost variant? I was trying to finish the implementation of this before this, but then I had to work on slides, and that didn't happen. But there's really nothing that still prevents me. I just have to finish debugging it. Basically, yeah, you can do this. I just have to I had to refactor a little bit parts of the library. But yeah, you can take a variant and you can do essentially a match, and then say, okay, if it's a double of that variant, do something. If it's a complex which has subparts, you can also decompose parts, etc., and drive your recursion further. It doesn't work right now in the version that is checked in there. But I'm like 99.9% sure I'll get this to work. So, all right. So some summary to take about the pattern matching. Let me see if I'm doing on time. Okay, I still have 8 minutes. Should be good. So some summary to take about the pattern matching is. It's intuitive. It's much easier and much easier to teach and understand. It has you can see in the code the direct show of the intent as opposed to like the boilerplate. You can do relational matching easily as opposed to have to do like stacks of visitors. You can do nested matching, which is you cannot do easily with visitors. There is no control inversion. You get local reasoning, so all your cases are in one place. So you get all that. It's not available as a language feature, and this can be abused. People can start using this in the cases where they shouldn't. Something where a perfect, like virtual function would have been ideal. Maybe people can start using pattern matching while they shouldn't. So you have to realize that the pattern matching in general doesn't solve what's called the expression problem, for those of you who heard it. So it still kind of limits it to your set of distinguishable cases in the same way the visitor does. So it's not fully open like virtual functions are. So that's why you still have to be aware of when to use one and when to use the other. When you are dealing with the open case, and when we are dealing with the closed case. This will still work with your multiple inheritance, with everything, like as long as it falls into the one of the cases or into the otherwise clause. You can have the otherwise clause, as you saw in some of the thing. As long as you can express it in that generic setting, that's okay. But what I'm trying to say is like this, you still have to be aware of when to use one and when to use the other. So the second alternative is open multi-methods. What's open multi-method? It's basically multi-methods plus open class extensions. Multiple dispatch is essentially virtual functions on multiple arguments. So instead of taking just the dynamic type of one argument into account when we do virtual function dispatch, we take a runtime type of several arguments to drive the same. What's open class extension is basically a possibility to add virtual functions outside of the class. So, and that's something people request a lot. So I would say like there is way more use cases for the open class extension than for the multiple dispatch. And there were like studies. It was done on Java, but basically the outcome of the study was that multiple dispatch on two arguments is used like in probably like 5% of use cases or something, and then it declines like super fast even further. Like on 3 arguments, it was probably like 2 or 3% of use cases, and then like even less. So. What you would typically care is like there is still a lot of use cases for the binary multi-methods, and the equality is what we saw. So like when you need to implement like deep equality, that's a typical example, or something that is on 2 arguments, but 3 is already much less. So examples, as I just said, of use of open multi-methods, equality, shape intersection is always mentioned, object interactions in games, like if you have some sort of like action system, like where you have actions applied to objects, that's also ideal for that. Why should you care? I mean, it's nice to be able to introduce virtual functions retroactively without having to change, and it's good to be able to do it on several arguments, at least on two, which is what we need. When is it useful? I would say like when you need to do interactions between objects. So most of the use cases for the visitors fall also here. Okay, so we demonstrate with experimental syntax that we did on top of EDG. To implement eval, essentially, what you will do is you will declare like it's what called the base multi-method, which is the first one, and you will say that one of its arguments is virtual. So instead of saying that the function is inside the class is virtual, now we are saying which argument should be treated as polymorphic argument. And you can mix polymorphic and non-polymorphic arguments. And then the other ones are treated essentially as the overriders for those. The semantics that we give in that paper is essentially we give the overload semantics taken at runtime. So let's say at runtime we will build the dispatch table, and we will, for each of the combinations, we will pick the most suitable overload available at compile time, as if all the overloads were available in one place. So this implements the entire eval using the multi-methods if they were available in the language. You can see that there is no need to foresee all the virtual functions. You can easily mix non-virtual and virtual arguments. It's still a little bit hard to reason locally about, because technically this don't have to be all in one translation unit. They can be scattered around. And there is still kind of semi-inverted control, because with pattern matching, like if you are inside of a loop, you can like save some state, like drive something using that state. Here you will have to pass that state explicitly into the call. So that's why I don't call it exactly as a control inversions, but it's kind of halfway there. The same thing if you were to implement equality of two terms using multi-methods, we will just essentially declare an equal multi-method equal, where both arguments are treated for dispatch. And then we essentially, by default, we say they are not. And this is a specific case where we're interested in the diagonal. But like, for example, in case of match function implementation, they are not exactly symmetric, because we're interested like when variable is on the left and anything on the right. So you can do it other ways. The only thing you will have to be aware is that this is subject to ambiguity. So like you can have ambiguities with the overloading. You can get those essentially now at link time once we try to build the table, and you will have to resolve those ambiguities, which is why I think presence of ambiguities can be kind of a negative factor for their adoption, because it might be less intuitive. And some of the ambiguities you may not be in the control of, like if, for example, if your new overriders come from different DLLs. Then essentially our choice was like to make like a non-deterministic choice of one of them, because but still type safe choice. So like all of them will be still type safe, but we will just pick one without specifying which one. It works with the current C++ object model with multiple inheritance, with virtual functions and everything. So to summarize the multi-methods. They provide you both extensibility of functions and classes. They are super fast, as we will see in the next slide. They are easy to teach. People get this once people know virtual functions, people get this easily too. General, they allow you to do relational checks. As I said, like the disadvantage is they are subject to ambiguities. They require changes to both linker and loader, and no local reasoning and semi-inverted control. So just a bit of the performance numbers I was showing. So the basically the things at the bottom is the number of arguments 1, 2, 3, and 4 on which we are doing this this dispatching. The red one is the visitor design pattern. The middle one, the blue one, is the pattern matching, the type switch essentially on top of which the pattern matching is based. And the last one is our implementation of the multi-methods. So you can see that multi-methods win regardless of the number of cases. I mean, almost always, because they essentially the table lookup. So that's why. But you can see also that visitors are slower. I mean, we are comparable to visitors like in the case of the single argument, but we become faster than visitors in case of multiple arguments. Of course, probably the only relevant is 2, but still. As it gives you. And if you look at the papers and CppCon presentation where we have more data, we show like in which other cases, like how we compare to other languages like Haskell, XML, and Sync. Yeah, it's actually switched by itself. What these slides presents is essentially we listed all those nice features to have, what we would like extensibility of functions, extensibility of data, whether it's type safe, does it support multiple inheritance, does it support relational reasoning, nesting, like nested checks, is it retroactive, can you add it retroactively, does it have like local reasoning, does it have control inversion, etc. So pluses are good, minuses are bad, meaning like you don't have it in that feature. So you can see that the stars is kind of like, wait, where do I have the star there? Redundancy checking. Okay, so functional languages have redundancy checking, which is extremely useful, but they can do it because their set of cases is closed. Here we deal with open case because you can always add new classes. So you can't have the exact redundancy checking, or at least like it's not in the form that is available in functional languages. But you can have some sort like at least check whether you have otherwise clause or whether you have something like that. But you can see pattern matching handles most of those, and it's comparable. Those numbers actually with pattern matching, like if you just take the type switching part, it's very similar to the visitor design pattern. So. And just as a conclusion, I'll remind again the Dr. Stroustrup slide. And yeah, as we saw, visitor design pattern unnecessarily complicates things. It's extremely hard to teach. It's expert friendly actually. While open pattern matching, still keeps things simple and ignore the quirks of the syntax. It will be even simpler in the actual language proposal. It does not sacrifice the performance. Easy to teach. And well, right now available to try as a library solution. We compile with I was after CPP now. I was trying to make sure it also builds with Clang, so it now builds with Clang, GCC, and Visual C++. If you want to try it, if you have any specific compiler you want me to make it work with, just send me an email. And yeah, and open multi-methods, they are the ultimate performance, and they still are extremely simple, and they integrate well with the rest of the language. And so I'll take questions.
What about dynamic linking?
So in the case of multi-methods, or in the case of pattern matching, so in case of the multi-methods, yeah, we considered that. So we talk about dynamic linking. That's why I was saying like it requires changes also to loader, because in some cases you need to be able to build some of those tables at load time, but it's doable. And the only, like with regard to ambiguities, you can have two DLLs that have perfectly unambiguous sets of overriders, but when you load them together, the set becomes ambiguous. And at that point, like there is nobody to resolve that, so we essentially will pick one implementation or the other just deterministically, but in unspecified way. The pattern matching, yeah, your classes can come from new DLLs and everything. It will just work. It will fall into the case for the most for the least derived type that is available in the case statement or in the first. So it still works with new classes coming from new DLL, and you can implement new functions in DLL, so it works. Does that answer your question? Okay. Any other question? Yeah.
So expression is such a popular construct of all languages. Besides the technique you introduced here, as you are aware, in other technology as of the cross design and trading personal.
You mean other use cases for?
Technology as a solution to capture react such as the regular expression classified and the retroactive.
You mean well? So other technologies to be able to deal. I mean, there are dedicated languages. There are like languages that deal with trees, and to be like, if you look even like at something like XSLTs or like XDues, those are the languages that have the constructs to essentially deal with trees, and you can try to mimic that kind of functions. You know, you can build your own DSLs, but I know, like, if there is something like, you know, like widely, like, at least doesn't come to my mind immediately, you know, like what would be the next best hammer to deal in all the cases with these kind of applications. Any more questions? So nothing is clear, or? All right, thank you very much.